Okay, so we're still going to be dividing radicals, kind of using that, or not kind of, really using that strategy that we talked about yesterday because it saves us time in our factor tree, not having to deal with such large numbers and simplifying over and over again. But what we're going to do differently is sometimes when we simplify, we end up with a radical in the denominator. And technically, that's not simplified. So we're going to talk about something called rationalizing the denominator. That means if whatever the denominator, the radical is in the denominator, I'm going to multiply whatever that radical is times both. So follow with me if you will, okay? For instance, number 13. At first glance, there's nothing to do. Like the radical simplified, 7 can't break up any further, and 4 is a 4. Like I'm not going to break that up because it's just a 4. It's not a radical. But my answer is improper or not right because of the radical in the denominator. So what's called rationalizing the denominator means I'm going to multiply both the denominator and the numerator by that radical of 7. And the reason why it doesn't matter mathematically is because this is technically just 1. Square root of 7 over square root of 7 is just 1. So the math still works out. But what does this do? Well, so for instance, think about what we did with multiplication. We technically look at it as 7 and 7 don't branch off, but they are a pair. And whenever they make a pair, that pair comes out of the radical. So my denominator is just 7. Weird, I know, and I'll explain it a different way. And then the numerator is 4 with the remainder of 7 because you can't break that up any further. But what it's done is just made it to where the denominator doesn't have a radical. That's literally it. Now, another way to think about this is, well, like if this didn't make sense, like how did square root of 7 times square root of 7 equal 7? Well, think about what 7 times 7 is. It's 49. And the square root of 49 is 7, so there wouldn't be a remainder. So that's another way. Let's look at number 14. So again, 5 and 2 don't branch off any further. There's no canceling like we did yesterday. But because the denominator has a radical, we're going to multiply the radical 2 times both the numerator and denominator. All that does essentially in the denominator is 2 times 2. That makes a pair, so that just brings out the 2 with no remainder. Again, it's like saying 2 times 2 is 4. The square root of 4 is 2, so it's a perfect square. Yay. Now, what I do at the numerator is, yes, these don't branch off. Yes, they don't have pairs, but 5 times 2 is 10, so I just have a radical of 10. That's it. Let's do another one. So number 15. First things first, the square root of 81 is technically a perfect square, which means it just has a pair of 9s that would come out. And then I still have this radical 2. But since I can't have a radical of 2 in the denominator, I'm going to multiply both the numerator and the denominator by the square root of 2. So essentially all that does is 2 times 2 is 4, square root of 4 is 2, so it just brings out a 2. And then there's nothing really to do in the numerator except 9 times 1 is 9, and then it has a remainder of 2. Again, the purpose of rationalizing the denominator just means your answer cannot have a radical in the denominator. That's the only thing it does, okay? Let's try number 16. So first we're going to do what we did yesterday, which means I branch off my numerator and denominator because these are not perfect squares. So this is 2, this is 3. This is 6 and 3, and this is 2 and 3. If you remember what we did yesterday, we looked at where we could essentially cancel. Well, here I can cancel a 2 and a 2 and a 3 and a 3. Now, since I don't have any remainders in the numerator, reminder is just means there's an invisible 1 in the numerator. But in the denominator, I took those canceled out, but I still have this remainder of 3, so I have a radical of 3. Nothing wrong with this to me, but they take it one step further and call it rationalize the denominator, which means we're going to multiply both the denominator and the numerator by the radical of 3. Now remember, all this does is essentially take away the radical. So the square root of 3 times the square root of 3 is just 3. Now what I'm left with the numerator is just 1 with the remainder of 3. So that's where essentially the radical moves to. Think of it like the negative exponent law. You cannot have a negative exponent at all. So to make it a positive, you move it to the numerator. So in this case, but let's look at number 17. Again, nothing to do with branches. 3 and 2 wouldn't cancel. But because the denominator has a radical, I'm going to multiply it times 2. Same thing up here. Again, all that does is essentially take away the radical. So 2 times 2 is 4. The square root of 4 is 2. But then in the numerator, 4 times 1 is 4. And since 3 and 2 don't branch off any further, 3 times 2 is 6. Now, this is where I have to see if I can simplify any further. The 4 over 2 simplifies to 2. So my final answer is 2 with the remainder of 6. So a lot of simplifying here. But let's look at number 18. Again, nothing I can do besides the square root of 4 is a perfect square. So that means it's just 2 over 10 with the remainder of 3. Again, my issue here is I have to rationalize the denominator, so I'm going to multiply the numerator and the denominator by the radical of 3. Again, remember, all that does is essentially get rid of the 3's, but here I have 10 in front, so 10 times 3 is 30. And then I still have 2 with the remainder of 3. Again, I can simplify 2 over 30 one step further to make it 1 over 15, but there's still that remainder of 3 in the numerator, so that's my final answer. Keeping going, if I look at number 19, first things first, I do branch off here. 12 is 4 and 3, 4 is 2 and 2, 10 is 5 and 2. I look to see if I can essentially cancel anywhere, which here I can cancel the 2's. Now I cannot simplify any further than that, but I do have a remainder of 6 here, so 5 with the remainder of 6. And then all I have is a remainder of 5. But then if I look at the denominator, it's not, I have to rationalize it, so I'm going to multiply by 5. And then what I look at is my 5's would essentially disappear the radical, so 5 with a remainder of 30. If I try to take 30 further, it would be, actually 30 is factorable. If I take 30 further, it would be 6 and 5. Oh, no, it wouldn't. Sorry, it wouldn't simplify further. But I can simplify the 5 over 5, and 5 over 5 is 1, which is just means my final answer is a remainder of 30. Weird one. All of these are weird, to be honest. But number 20, again, I can't factor anything out because the only radical involved is 6, but I have to rationalize the radical by multiplying by the radical of 6, which, remember, just takes out a 6. 6 times 5 is 30. And so I have 2 with the remainder of 6 in the numerator, but the 2 over 30 simplifies to 1 over 15, which we saw in number 18, with the remainder of 6 in the numerator. If I look at number 21, first things first, there's no branches to branch off and simplify, but I need to multiply the denominator and numerator by the radical of 2. This opens up this to 2 times 6, which is 12. I still have a 4, but this time with a remainder of 10. And then I look to see if I can simplify the 4 over 12. 4 over 12 simplifies to 1/3, but I still have that remainder of 10 in the numerator. Again, just to get more practice, again, number 22. Here, I can branch off the 6, which would be 2 and 3. That would essentially cancel my 3's here. So I have no remainder in the numerator, but I do have 3 with a remainder of 2 in the denominator. Again, the issue with this answer is the denominator has a radical, so we're going to simplify that by multiplying the radical by 2 on both the numerator and denominator. This opens up the 2. 2 times 3 is 6, and then on the numerator it'd be just 2 over 2. But the 2 over 6 simplifies to 1 over 3, and I still have that remainder of 2 in the numerator like that. Number 23, again, I could branch off the 8, but it wouldn't simplify the 3 at all. So I'm just going to multiply everything by the radical of 8. Here it opens up the 8. 8 times 2 is 16. And then on the numerator, 8 times 3 is 24. And then 6. Technically, this, I don't know how that happened. 2, 4, 3. The 24 can be simplified because it has 12 and 2, then 4 and 3, and then 2 and 2. So it would have a pair of 2's. 2's come outside the radical, so that would be 2 with a remainder of 6 over 16. 2 over 16 simplifies to 1 over 8 with a remainder of 6, like that. Number 24, I can't factor out 12 any further to simplify the 5, but I have to multiply everything by the radical of 12 to rationalize it. That would leave that open to 12, 4 with a remainder of, 5, 60. But then I can simplify this 2 ways. The 60 can simplify to 6 and 10, 2 and 3, 5 and 2. The pair of 2's would come out, which would be times 4, which was 8, with a remainder of 15 over 12. The 8 over 12 can simplify further to be 2 over 3 with the remainder of 15 still in the numerator. Again, not the easiest or simplest of lessons because of the rationalizing part, but ultimately it just means you cannot have a radical in the denominator.